Hello and welcome to this video tutorial. Today, we will be going over thermal expansion and contraction of matter, which is a phenomenon that occurs in response to temperature change. I will quickly go over an example and show you how to calculate the length change of an aluminum part due to a temperature swing, and then solve the same problem using SolidWorks simulation. Every material has an associated and unique coefficient of thermal expansion and contraction, abbreviated as CLTE, which is a rate at which a material expands and contracts in response to variation in temperature at constant pressure and without reaching a phase change. There is a direct positive correlation between CLTE and the amount of physical change, meaning the induced thermal movement of a material with higher CLTE will be greater than that of another material with lower CLTE under the same temperature change and conditions. In this study, we are given a 1/2 inch thick by 6 inch long 1060 aluminum alloy cuboid that is only restrained at one end and free to move on the other end. Think of a cantilever beam. The part is exposed to a rising temperature, which was increased from 73.4 F or Fahrenheit to a final temperature of 392 Fahrenheit. This type of material has a CLTE of 1.33 times 10 to the negative 5 inch per degree Fahrenheit. That means that every inch of this material will move by 1.33 times 10 to the negative 5 inches for every degree Fahrenheit of temperature change. To calculate the dimensional change to the given temperature swing, we will be using this formula. As presented here, the change in length is a function of CLTE, initial length, and temperature swing. To get the numerical value, let's plug and chug the given information. We will be using 1.33 times 10 to the negative 5 inch per degree Fahrenheit in place of alpha or CLTE, 6 inches for the initial length, and then subtract 73.4 Fahrenheit from 392 Fahrenheit to get the delta T. That yields 0.025 inches expansion, or 25 thousandths of an inch. Pretty straightforward. Now, let us solve the same problem using SolidWorks simulation. The first thing we're going to do is to design the 3D model, which is a straightforward task since this is a simple shape. We begin by starting a new part and sketch a rectangular shape. Insert the dimensions. And extrude to 6 inches long. We can assign the material directly here, or do it when the simulation is started. Let's assign the material here from the material library under the aluminum alloys folder. To define the material, under the design tree, right-click on the material and select Apply Material. A material window opens. Look for the 1060 aluminum alloy under the aluminum alloys menu. Select and apply. Remember, when the material is defined for a SolidWorks part model, the material is automatically transferred to the simulation part, and there is no need to reassign the material properties again. To access the Fixture Property Manager, right-click on Fixture and then Fixed Geometry. Under this window, you will be able to select the end at which the restraints are applied. Since we are dealing with temperature changes, we need to define and apply the initial and final temperature of the model part. And to do so, right-click on External Loads and select Temperature. This will open up the Temperature Property Manager. Because we are assuming steady state, meaning the model part temperature is uniform and steady for both the initial and final temperatures, instead of selecting the faces, let's choose the entire solid body. Make sure the units are property adjusted too. Because we need the temperature change to take place in order to induce thermal movement, we also need to specify the zero strain temperature, or the initial temperature. This is the reference temperature at which no movement occurred. Now we're ready to mesh and run the simulation. In SolidWorks, you have the ability to make edits so that the results are presented to your preferences. Notice the stress levels at the restraint face. They have surpassed the yield stress, which indicates that this material is not suitable for this application. As we can see in the simulation results, the maximum expansion occurred in the left direction and was calculated to be 26 thou at the given temperature change, which is the same expansion as what we calculated numerically at the beginning of the video. The thousandths of an inch difference was due to rounding the CLTE in our hand calculations. As you can see here, you have the ability to visualize the displacement in vector format. In conclusion, we have calculated the expansion of a given part by simply using the material CLTE and by defining the temperature change. We have also shown that SolidWorks simulation is a great tool to analyze such problems in greater detail. These type of engineering tools allows you to make sound engineering decisions quickly and efficiently and decide on whether the material is safe to use under known conditions. So make sure you take advantage of their potential.